This is part 2 of the ideal gas law notes, and in this part we're going to be working through some problems. These are the same problems that are in your note pack. We're going to work through actually 4 of these problems. I will be skipping one of them. Let's take a look at number 1. Now, when you read through your problems, you're going to need to be able to identify your gas law, and one way that we do that, and this is what I want everyone to always show, is make sure that you show your listing of your givens. There's certain words that you will see that will let you know it's ideal gas law. Remember, ideal gas law is P times V equals N times R times T. Ideal gas law allows us to find moles of our gas. So one thing that you will see in your problems that will sort of let you know it's an ideal gas law problem is you'll either see moles, grams, molar mass, or molecules mentioned in the problem. So this says a sample of hydrogen gas has a volume of 8.56 liters and a temperature of 0 degrees Celsius and a pressure of 1.5 atmospheres. It wants you to calculate the moles, here's how we know it's Fibner, of hydrogen gas present in the sample. So when you list your given, PV, NRT, I remember the order of these in the formula because if you look at this, it looks like it says Pivnert. I know that's not a word, but that will help you remember the formula. So for this gas law, remember all the units are very specific. So the pressure has to be in atmospheres. Notice here our pressure is 1.5 atmospheres, and that is the proper unit for pressure. The temperature is in 0 degrees Celsius. Now we can never leave our temperatures in Celsius, so you have to add 273, and that's going to give you 273 Kelvin. Then it wants you to find moles. So I'm going to put a question mark there. I'm looking for moles. And this is of hydrogen gas. And it also says that we have a volume of 8.56 liters. So our volume is in units, and that's exactly what it needs to be in. Remember, R is a constant, and the value for R is 0.08206. Now, the reason we're making all this fuss about the units on this problem, this type of gas law problem, is because of R. R has units, and the units for R are liter times atmospheres per Kelvin times mole. So you can see liters here, it's got to cancel with liters here. Atmosphere with atmosphere, Kelvin with Kelvin, and mole are matching up. Now I'm going to go ahead and rearrange this formula to isolate my variables since I'm solving for moles. You do not have to do this, but this is something I want y'all to work towards. So the formula, if you isolate this and solve for moles, you're going to need to divide by RT. So the formula becomes V divided by RT. I'm going to plug straight into the formula. Pressure is 1.5 atmospheres. The volume is 8.50 every time as I plug in because I have them over here. But for this first example, I want to do so just to reinforce the reason that our units have to be specific for this gas law. Notice atmospheres cancels with atmospheres. Liters cancels with liters. Kelvin divides out with Kelvin, and you're left with moles. And moles is what you were solving for in. So you know you set your problem up correctly if your units are all jiving. So you're going to plug in. And we need to round this to 2 sig figs because our pressure has the least sig figs here. Everybody plug that in. I'm going to go ahead and go along with the video so I don't get cut off, hopefully. You can pause the video in the middle of the problems if you need to, just to give yourself time to work them out and verify that you are getting the same answers. 0.57 moles is your answer here, and this is of hydrogen. Okay, I'm going to skip number 2, and I'm going to go straight to number 3, and that's because these are very similar. So in the notes, let's go to number 3. Number 3 says you have a rigid hollow sphere containing 680 milliliters of helium gas. It says it's heated from 300 to 600 Kelvin. The pressure increased to 17.8 atmospheres, and it says how many moles of helium are in the sphere, how many grams of helium are in the sphere. So there's 2 things they're wanting here, moles and grams. But when we see moles, we know it's an ideal gas law problem. So we're going to list our givens, P, V, N, R, T. Of course, we always know R is 0.08206. liters per Kelvin mole. All right, so now it says 680 milliliters, so that's the volume. Now, remember, we have to have our units to cancel. So in order for R to cancel, the liter to cancel, this has to be converted to liters. So we're going to use our conversion factor. Many kids have dropped over dead converting metrics many nights. And so we're going to be using over dead converting metrics. We need to go from milliliters to liters. So take your decimal, move it 1, 2, 3 places backwards. So if you move it back 1, 2, 3, you're going to get 0.68 liters. Remember, this has 2 sig figs, so keep it 2 sig figs here. So 0.68 liters. Then it gives the temperature in Kelvin, but y'all, they've given 2 temperatures, so which one should we use? Well, let's look at it. We need to use our context clues. It said the gas was heated from 300 Kelvin to 600 Kelvin, and the pressure of the gas increased. Now remember, you've got to be using the condition for temperature and pressure that match. Well, if it increased to 17.8 atmospheres, which is our pressure, 17.8 atmospheres, that means you have to use 60 at the higher temperature. So that's the temperature we're going to use, 600 Kelvin. And let me point out that has 1 sig fig in it. So now we're going to find for moles. But don't forget, they also want you to go to grams of helium. And there's 2 answers they're wanting here. But we have to first find moles. So again, N is equal to PV divided by RT. All right, the pressure, plug it in, 17.8 atmospheres. The volume, 0.68 liters. R, 0.08206 liter atmosphere per Kelvin mole. And the temperature was 600 Kelvin, and there's no decimal there. This is going to allow us to find our moles of our gas. And when you plug in, solving for your moles, we're going to round this to 1 sig fig. So you're going to get, when you round that to 1 sig fig, 0.2 moles of helium. Now remember, when you have a calculation where you're going to take this answer and then do something with it to convert, don't clear your calculator out. This is what you write down for purposes of sig figs in our answer, but please don't clear your calculator. Go ahead and keep that number stored in your calculator. So now we're going to convert 0.2 moles of helium. And they want us to go to grams. So this is where our dimensional analysis comes in. All the stuff we learned back in chapter 10, we first learned how to go from grams to moles. So we need the molar mass of helium. And helium's formula is just He. So use your periodic table and find helium. Its molar mass is 4.00 grams per mole. This lets the moles divide out. And we're going to round this to 1 sig fig because that's our least. So that's going to give you for your final answer your mass, 0.8 grams of helium. All right, let's move on to example 4. Example 4 says a child has a lung capacity of 2,200 milliliters. How many grams of gas, of air, do her lungs contain at a pressure of 0.34 torr and a normal body temperature of 37 degrees Celsius? And they even go on to say, assume the molecular weight of air is 29 grams per mole, because remember, air is a mixture. So P, V, N, R, T. And since it says grams, that's how we know that we're going to need to use Pivner. So we're going to find moles first, moles of air first, and then we're going to convert that to grams of air, which is the final thing they want. Now, it says the volume is 2,200 milliliters. Now, remember, for this gas law, you got to convert to liters for your volume. So we're going to be using, again, over dead converting metrics. And we're going to move our decimal backwards 1, 2, 3 places. That's going to give you 2.2 liters. Here they give us the pressure is in torr, so 0.34 torr. Now, can we leave our pressure in torr for this gas law? No, we cannot. So we're going to convert, and I don't have a lot of room here, but remember, to convert, we divide by 760. We learned that 760 torr is equal to 1 atmosphere. We have to go to atmospheres here. That's going to give us, for our pressure, 4.5 times 10 to the negative 4 atmospheres. I'm going to stop this video right here and pick up in a separate video because my time limit is approaching. So we're going to pick up right here in the next video.